of the inversion of the Laplace in the Z transforms with a formal expression. Yesterday we had looked at the inversion of the Laplace transform, and we had in fact just mentioned without proof that the expression for the inverse was as follows. If xt had the Laplace transform xs, then xt could be expressed in terms of the Laplace transform as 1 by 2 pi j integral over any c xs e raised to the power st ds, where the contour c is a vertical line in the region of convergence. Now here I must emphasize that when we talk about a vertical line in the region of convergence, the vertical line must lie entirely in the region of convergence. So it cannot be at the boundary of the region of convergence. Okay? We would like to use a similar expression or build up a similar expression for the case of the Z transform. In fact, what we shall do here, in the case of the Z transform, it will be a little easier. Here again, if you look at it carefully, a special case of this is the expression for the inverse Fourier transform. So in particular, just to recall, in particular, if the imaginary axis belongs to the ROC, then we have xt is 1 by 2 pi. I mean, it's a special case of this, where c is the imaginary axis, and in that case you have s is equal to j omega, right? So you have s is equal to j omega. So this becomes integral minus infinity to plus infinity x j omega, which is essentially the Fourier transform, e raised to the power j omega t d omega. All right, this is essentially the inverse Fourier transform expression. All right. So one could think of this expression for the inversion of the Laplace transform as a generalization from the inverse Fourier transform expression, which essentially says that you can reconstruct a vector from its components by multiplying each component by a so-called unit vector in that direction. So you might want to think of each of these e raised to the power of st's as unit vectors in the coordinates s. Right, for each s there is a so-called, I agree this is not absolutely accurate, because what do you mean by a unit vector and so on, but that idea does carry over to functions. So one can think of it as a generalization of a unit vector, xs as a generalization of a component. So essentially this expression says component multiplied by unit vector in that direction summed up over all the components. And of course here what we are saying is that you can find many different components xs all over the region of convergence, but you don't need all of them to reconstruct xt. You need those components that lie along any vertical line in the region of convergence. It is enough. Those are sufficient to reconstruct xt from xs. All right. Now we wish to establish something similar for the Z transform. So this time again, let's try and go from the discrete time Fourier transform and generalize the Z transform. So, recall that the discrete time Fourier transform was expressed as follows. If you had a sequence xn, its discrete time Fourier transform was expressed as x omega given by n e raised to the power minus j omega n. For a moment, let us interpret this expression from a slightly different perspective. Let us think of xn as coefficients now for a moment. For each n, xn is a constant, it's a coefficient. And each of these e raised to the power j omega n are phasors, but in omega. So, you can think of them as rotating as you change omega, not n. So, see n for a moment, let us think of n as the angular velocity, right. For every integer n, there is an integer angular velocity there. So, as omega varies over an interval of 2 pi, this phasor undergoes n cycles. Now, n can be positive or negative. It means it could either undergo n clockwise cycles or n anti-clockwise cycles. Now, let us multiply this phasor capital X omega by a phasor e raised to the power j omega m. What does it do? This is a linear combination of several such phasors. This product acts on each of them. So, you see, you might think of it like this. You might think of multiplication by e raised to the power j omega m as a handle which rotates with a velocity of m as you change omega. So, each of these phasors now suffers, a counter motion. You see, you can think of each of these as a rotatory motion and this one as a counter rotatory motion with a velocity of m. So, the net velocity of each of the phasors now becomes n minus m. In fact, that is very easy to see. This simply becomes summation on n x n e raised to the power j omega m minus n. All right. So, again now you again have a large number of phasors summed up with appropriate amplitudes. Now, what do you do next? You average these phasors over a cycle. Now, you see, any phasor that is still rotating will have a zero average, which means when m is not equal to m, when m is not equal to n, that phasor has a zero average over a cycle. What is a cycle? A cycle is when omega varies over an interval of 2 pi. Any interval of 2 pi is fine. It could be from 0 to 2 pi, it could be from minus pi to pi, right? And therefore, if we consider integral x omega e raised to the power j omega m d omega, that is what averaging means. This would be, now the integral is over any interval of 2 pi. This notation denotes any interval of 2 pi. It could be from minus pi to pi, 0 to 2 pi, and anything else, right? And divide by 2 pi, that is an average, right? This is the same thing as integrating this over the same interval of 2 pi and dividing by 2 pi here. Because xn is a constant. And if it's since this integral is finite, it can be taken into the summation. Yeah. Now look at this integral. You see, e raised to the power j omega n minus m or m minus n d omega divided by 2 pi is equal to 1 when m is not equal to n, when m is equal to n, and 0 else. This is very easy to evaluate. This integral is very easy to evaluate. It's of the form e raised to the power of at, right? So one can evaluate this very easily. The interpretation is that if you have a rotating phase and if you rotate it, if you average it over a cycle, then the average is 0. But when m is equal to n, that phasor is curtailed. So it stops rotating and the average is a constant equal to 1. So what happens in this process of integration? All other terms drop out and the term m equal to n remains, right? So this gives you simply x of m. So in fact, this is the expression for the inverse discrete time Fourier transform. We had the discrete time Fourier transform here, and this gives us the inverse because we can get back the points of the sequence from capital X of omega by this expression. So let's write down the expression for the inverse discrete time Fourier transform once again. Inverse discrete time Fourier transform. This is the abbreviation. Sorry. Yes. You see, each e raised to the power j omega m. The question is, how do you treat this as a rotating vector? Well, if you look at the term e raised to the power j omega m, and if you think of it as varying as a function of omega, it's a complex number of unit magnitude rotating with a velocity m, right? When you have, see, if you have e raised to the power j, let's say at, a being a real number, this is, and if you think of t as the variable, then this is a phasor rotating with an angular velocity of a. Now here think of omega as the variable. So it rotates with an angular velocity of m as you change omega. That's what I'm saying, right? So you must think of it as a phasor rotating with an angular velocity of m, thinking of it as a phasor on omega, right? And what we are doing here is to, see, you can think of it like this. Capital X of omega is a sum of many such phasors. And this multiplication by e raised to the power j omega m is like applying a handle which rotates in the opposite direction with a velocity of m. So it will hold back exactly that phasor which rotates with an angular velocity of minus m. That will have net zero velocity. And all other phasors will still have a velocity of m minus m, right? So all others will still give a non-zero, will give a zero average, but just that phasor which has a velocity of m, or rather minus m, will give the average of 1. All right, that's what we are saying. So the inverse TTFT expression is x of m is given by 1 by 2 pi integral over 2 pi capital X omega e raised to the power j omega m d omega. That's what we have derived here. Yeah. So this is essentially getting back the sequence from the discrete time Fourier transform, right? So notice there are some important differences here between the expression for the inverse discrete time Fourier transform and the expression for the inverse continuous time Fourier transform. One important difference is that the integration is over any interval of 2 pi. Now this is to be expected because the discrete time Fourier transform is periodic with a period of 2 pi, right? The other thing, of course, is that there is a division by 2 pi, but that is similar to the case of the continuous time transform. That's not really an important difference, right? But there also you have a factor of 2 pi. Needless to say, if you replace capital omega by the Hertz frequency, then the factor of 2 pi can be removed, right? So one can write e raised to the power j 2 pi fm, and then one can remove the factor of 2 pi. Yeah. Anyway, the point is we'd like to generalize this expression to the Z transform. So, even now the first thing that we need to ask ourselves is, what is the relation between the Fourier transform and the Z transform for the case of sequences, or in other words, what is the contour, what is the curve in the Z plane that gives us the discrete time Fourier transform. Yeah? Well, let us ask ourselves, what is the Z transform of the sequence? The Z transform is summation on n x n e raised to the power minus j omega n. I am sorry, this is the Fourier transform, I am talking about the Z, so z raised to the power minus n. How would I get the Fourier transform from here? By replacing z by e raised to the power j omega. Now, in the z plane, what does this mean? This means that we are working with those z's that have a magnitude of 1, an angle varying all the way from 0 to 2 pi. So, what is the contour or what is the curve that we are talking about in the z plane? The unit circle or the circle of radius 1, right. So, this is the unit circle. In fact, in the z plane, we can denote it in this way. This is how the unit circle is denoted. And at omega equal to 0, we are here. As omega goes from 0 to 2 pi, we rotate along the circle and return here. And as we expect, this is, the whole frequency axis is periodic with period 2 pi. So, when we rotate, we keep getting the same points. Yeah? In other words, vertical lines in the S plane translate to circles in the Z plane. That is not too difficult to see. In fact, if we write down the relation between the S and Z variables, we have Z is of the form e raised to the power st, right. So, if you look at a vertical line, what do you mean by a vertical line in the Z plane? In the S plane, a vertical line in the S plane is S is equal to sigma 0 plus j omega, right. So, we have Z is equal to e raised to the power sigma 0 t into e raised to the power j omega t. So, clearly the magnitude of Z, you see, how do we get the contour or how do we get the curve? By eliminating the unknown variable or eliminating the variable part of it. Yeah? So, mod Z is e raised to the power sigma 0 t, which is a constant. So, this is a circle centered at the origin. Yeah. So, therefore, a vertical line in the S plane maps to a circle centered at the origin in the Z plane. This is a very important observation, and therefore, a lot of things that we have been saying about vertical lines should carry over to circles centered at the origin. In fact, in the Laplace transform, regions of convergence lie between two vertical lines in the S plane. One of those vertical lines could be at minus infinity or at plus infinity, right. So, the extreme could be that one of the vertical lines is the extreme left or extreme right vertical axis. But in general, it is quite correct to make a statement about the Laplace transform that since the region of convergence depends only on the real part of S, it lies between two vertical lines in the S plane. What is the corresponding statement for the Z plane? The region of convergence lies between two disks or two circles, both centered at the origin. Right? So, in general, the region of convergence, yeah, lies between two circles. So, it might be visualized in the following way. This is the Z plane, then this circle and this circle, respectively of radius R1 and R2. So, the ROC is of the form mod Z is between R1 and R2. And of course, needless to say, either R2 could be infinity or R1 could be 0. Right? So, it could happen that R1 is infinity, R1 is 0 or R2 is infinity, just as for the case of the Laplace transform. Right? So, in particular, if the region of convergence includes the unit circle, then the Fourier transform of that sequence is defined. The discrete time Fourier transform of the sequence is defined, and we know how to invert it. Right? But it could happen that the unit circle is not included in the region of convergence. In that case, how can we take inspiration from the expression for the inverse DTFT to invert the Z transform? Right? So, let us write the inverse DTFT in the language of Z. Right? So, let us look at the inverse DTFT and write it in the language of Z. What is inverse DTFT? It tells you that Xm is 1 by 2 pi integral. Now, I'll write integral over 2 pi, which, I'll say it's an integral over the contour C. I'll explain what I mean by that. Capital X of Z with Z put equal to e raised to the power j omega, right? Now, the next term is e raised to the power j omega m. Let me write it. But then let me read, see, e raised to the power j omega is Z. So, let me write this as Z raised to the power of m. And then you have a d omega, but I don't want a d omega, I want a dz. So, how will I get a dz? Let us write dz. dz would be j e raised to the power j omega d omega. So, in other words, d omega would be of the form minus j or 1 by j z inverse dz. Can you see that? Yes? Can you see that? Because when you take e raised to the power j omega on the other side, it's e raised to the power minus j omega, that's z inverse. So, I can write as minus j z inverse dz. Now, j is a constant, so I can bring that minus j outside here, right? And I can write this as z inverse dz. And here, now instead of writing integral over 2 pi, I write integral on a circle in the region of convergence, right? So, I write integral not over 2 pi, but integral on a contour C, where C is any circle centered at z equal to 0 completely in the ROC. Is that right? What's that? Yeah, I mean, it's centered at z equal to 0 completely in the ROC. So the radius must be strictly between R1 and R2, where R1 and R2 are the limits of the region of convergence. Yeah. As I said, in particular, if the unit circle is included, then one can take the unit circle here and get the inverse discrete time Fourier transform. So one can simplify this. One can write 1 by 2 pi j. Now you see here in the complex plane, we normally denote such an integral by a closed. So we write it this way. We write integral over a contour C. Now this is an example of a closed contour in the z plane, right? A closed contour, is a contour where you start from a point and return to the point. Yes. So xz, z raised to the power m minus 1 dz. Now you see, look at the expression, look at this expression. Well, the first thing that we notice about this expression is, of course, that it involves complex integration, and complex integration is normally not done in the manner of conventional real integration. We do it normally by using, assisting theorems, for example, the Cauchy's theorem of residues. So we would normally evaluate such an integral by using the Cauchy's theorem of residues, right? The other thing to notice is the interpretation of this expression from the point of view of vectors, right, or from the point of view of components. Though it's a little more difficult to do so here, we can still think of this as a kind of combination of the component along a particular z, right, multiplied by that particular, eigen function, right, z raised to the power of m. The only catch is that here there is z inverse. That z inverse is required to balance out the element of integration here, right. So although not, maybe there is a little difference between the nature of the integrand here and the nature of the integrand in the inverse Laplace transform, the philosophy is the same. You are multiplying the component by the corresponding unit eigenfunction z raised to the power of m, and then summing up over all such, eigenfunctions with their components. The only catch being that you need to take care of the element of integration here by introducing z inverse dz. I don't think we should drag that interpretation further than this point, right? Because, it's, though one can give it that intuitive meaning, one should not carry that intuitive meaning too far, right? In any case, the point that I am also trying to make here is that evaluating the inverse Laplace transform or the inverse z transform by using the inverse expression is normally a very cumbersome task. In either case, one needs to use ideas of complex integration. So the inversion of the Laplace transform, the z transform, is normally done by experience, right? Now let us take a couple of examples to illustrate the point. We are already familiar with the inversion of the Laplace transform by experience because we use it in networks. But let us go over an example still, and let us also bring out a parallel example for the z transform. Yes. So let us go back to the example of e raised to the power of 2t ut. We already know its Laplace transform, which is 1 by s minus 2 with a region of convergence, real part of s greater than 2. Now the first thing that I wish to emphasize is that the region of convergence is important because there could be another Laplace transform with the same expression but a different region of convergence. In fact, let us consider the Laplace transform 1 by s minus 2, but with a region of convergence real part of s strictly less than 2. Yeah? Where could we have got an expression like this? So, it is clear that we need an e raised to the power of 2t somewhere, but that is right. Instead of e raised to the power of 2t being present on the positive side of the t axis, we need to have it on the negative side of the t axis. So, let us investigate the Laplace transform of e raised to the power of 2tu minus t. Let us investigate this Laplace transform. Yeah? So, this of course would have the Laplace transform given by minus infinity to 0 e raised to the power 2t e raised to the power minus st dt. And that gives us e raised to the power minus s minus 2 into t divided by minus s minus 2. Is that right? Or 2 minus s. But the limits are from minus infinity to 0. And this time, since we need this to converge, what do we want about the argument? You see, we want this argument, I mean 2 minus s, to have a positive sign, right? So, real part of 2 minus s must have a positive sign. So, clearly that means the real part of s must be less than the real part of 2, which is 2. Is that right? This argument must have a positive sign, right? And of course, what is this integral in that case? So, it is minus, right? So, it takes this value. Is that right? This is the value of the integral. And therefore, we are almost there, but for the negative sign. Yeah? So, therefore, if we instead of considering e raised to the power 2tu minus t, if we considered minus e raised to the power 2tu minus t, we would have got 1 by s minus 2, right. So, therefore, our conclusion is that one by s minus 2 with a region of convergence, real part of s less than 2, strictly less than 2, has the inverse. Now, I am bringing in a new notation here, Laplace inverse, has a Laplace inverse given by minus e raised to the power 2t u minus t. All right. We would like to carry over an analytical example to the Z transform. So, let us investigate the term a raised to the power of n un and let us find out its Z transform, right. The Z transform will be described by summation n. Now, since there is a un here, the summation runs only from 0 to infinity. Yeah, a raised to the power of n, z raised to the power minus n. Which is summation n going from 0 to infinity, a z inverse raised to the power n. And here we have a geometric progression which would converge only if the common ratio is strictly less than 1. So, therefore, this would be equal to the sum of the geometric progression 1 by 1 minus a z inverse, provided mod a z inverse is strictly less than 1, which means mod z is strictly greater than mod a. Is that right? Yeah. Now naturally we need to justify our observation that it is important to specify the region of convergence, right. So we ask ourselves, suppose we had the same expression but with a different region of convergence. Now what could be the different region of convergence? Mod z less than mod a, right. So what is mod? So let's look at that possibility. In fact, now for a variety we shall follow a different approach to inverting the Z transform there. So let's consider 1 by 1 minus A Z inverse, but with a region of convergence mod Z strictly less than mod A, and let us investigate what the inverse Z transform is. So now, we'll use the following notation for the inverse Z transform. We'll write strip Z inverse. This is a notation to denote inverse Z transform. Yeah. Now in fact here what we'll do is we'll use the binomial expansion. Right? As I said, for variety, let's use the binomial expansion. That's one of the techniques for inverting a Z transform. So I wish to illustrate techniques for inverting the Z transform on the fly with examples. Yeah. So you see, since mod Z is less than mod A, what is it that is less than 1? You see, we need something that is less than 1 in magnitude for convergence, right? So what is it that is less than 1? Well, mod A inverse Z is less than 1 in magnitude. We need some kind of a less than 1 quantity for convergence. So let's rewrite this in terms of mod A inverse Z. So we multiply both numerator and denominator by A inverse Z. So we have A inverse Z divided by or minus A inverse Z divided by 1 minus A inverse Z. Can you see that? This is an alternate way to write this expression. I'm just rewriting the expression here in this fashion. Is that right? Yeah. Now since mod A inverse Z is less than 1, 1 by 1 minus A inverse Z can be thought of as a sum of a geometric progression, right, which is minus A inverse Z summation n going from 0 to infinity A inverse Z raised to the power n. Is that right? So we rewrite this expression in the form shown here, and we can recollect this expression by writing summation, it's minus summation n going from 0 to infinity. Now instead of A inverse Z raised to the power of n, it's A inverse Z raised to the power n plus 1. Yeah? Yeah, is that right? Another way of saying this is summation n going from 1 to infinity A raised to the power minus n Z raised to the power n. Is that right? That's another way of writing it. Is that right? I've just rewritten it this way. So now, you see, one can recognize this expression, or one can think of this expression as a Z transform of a sequence. What sequence? Right? The sequence, this is the Z transform, this is the Z transform of, and if you look at the expression, it's a Z transform of the sequence which is equal to A raised to the power n for n less than equal to minus 1, or rather minus A raised to the power of n for n less than equal to minus 1 and 0 else. Can you see that? Yeah, it's the Z transform of the sequence minus a raised to the power of n for n less than or equal to minus 1, yeah, and 0 else. Now, how do we capture this statement n less than or equal to minus 1 and 0 else? We need to do it through some kind of u, the unit step u. The only thing is, what should be the argument of the u, right? Now, consider u minus n minus 1. Let us consider this sequence. What is the sequence u minus n minus 1? It is going to be equal to 1 for minus n minus 1 greater than or equal to 0, which is n less than or equal to minus 1. Can you see that? And 0 else. Is that right? So, sequence q minus n minus 1 captures this statement. It's the state that this expression holds for n less than or equal to minus 1 and 0 else. So, in other words, what is our conclusion? The conclusion is that the same expression 1 by 1 minus a z inverse, but with a region of convergence mod z strictly less than mod a, has the inverse z transform given by minus a raised to the power of n u minus n minus 1. Is that right? Same expression with a different region of convergence gives us a different sequence. Yes. Question is, can you express it in terms of minus a raised to the power of minus n? No. This is in terms of a raised to the power of n. Either you can express in terms of a inverse raised to the power minus n, or there is no way to express in terms of a raised to the power minus n. Ask the question properly, use the mic.
Suppose we consider the function minus a raised to minus n u of n minus 1.
Yeah, but you see, in that case, there are two problems. One is that, well, I think the question is, can you express this in terms of a sequence? I mean, can you express in terms of a sequence which has u n minus 1 there, right? So, which is non-zero for positive n. Well, not really. You can check. See, the question is, all right, this is a good question, but let me answer it right away. It seems, or it's tempting to think that it should be possible to express the inverse Z transform, or to have an inverse Z transform which has non-zero points on the positive side of n. That's what we are saying. Well, now let's look at the Z transform expression and establish certain properties about the nature of the sequence given the nature of the region of convergence, right? So, I think we'll come to that general conclusion both for the Laplace transform as also for the Z transform. Well, the answer as such is no. It's not possible to find a corresponding. Firstly, for a given Z transform with a given region of convergence, the sequence is unique. Okay, so once you have a Z transform and a region of convergence, the sequence corresponding to that is unique. So, there is no possibility of finding some other sequence which has the same expression with the same region of convergence. Once you specify the region of convergence and the expression, the sequence becomes unique. Same thing for continuous time. The non-uniqueness comes only from only the expression. So, you have just the expression, there is non-uniqueness. But once you have the expression and the region of convergence, there is uniqueness. All right? Either in the Laplace transform, in the Z transform. So, that itself indicates that there would not be another sequence here. Now, the other comment that we would like to make is, what is the relation between the nature of the region of convergence? What do we mean by nature? See, nature refers to the kind of the placement of the region of convergence, right? And the nature of the sequence, right? So, we will come to a very simple guideline for that. Let me go back to the example which I took for the Laplace transform, right? So, I said there is the S plane, there is the point S equal to 2 here, which forms a dividing line. Okay. There are, if you take the Laplace transform, if you take the Laplace transform expression 1 by S minus 2, there are two possible regions of convergence. Either to the right of this is one possible ROC, or to the left of this, right? That is the other possible ROC. Okay. What was the corresponding function here? It was minus e raised to the power 2t u minus t, right? And what was the corresponding function here? E raised to the power 2t ut. Now, what kind of a function is this? This is a function which is non-zero to the right of t equal to 0. What kind of a function is this? It is non-zero to the left of t equal to 0. So, I might call this function right-sided. What is a right-sided function? A function which is non-zero to the right of some point. So, I call this function right-sided. And I call this function left-sided. Because it is non-zero to the left of some point. Now, you see a very beautiful coincidence in the nature of the Laplace transform ROC and the kind of function. A right-sided function has a right-sided region of convergence, and a left-sided function has a left-sided region of convergence. That is universally true for the Laplace transform. What do I mean by a left-sided region of convergence? I mean a region of convergence which includes the entire S plane to the left of a vertical line. So, if you notice in the Laplace transform that the region of convergence is to the left of a vertical line, entirely to the left, that means the entire S plane to the left of a vertical line, then the corresponding function is also left-sided. That means it is non-zero to the left of some point t equal to t0. And conversely, if the Laplace transform has a region of convergence which is to the right of a vertical line, entirely to the right of a vertical line, then the function corresponding to it also is a right-sided function, namely it is non-zero to the right of a point t equal to t0, right? What is the corresponding, now what happens? You see, the region of convergence need not be left-sided or right-sided. It can be between two vertical lines. We shall come to that possibility later, after we look at the corresponding possibility for the Z transform.
Can we say that if we take the complement of the region of support in the line domain, in the Laplace domain we have to take the complement of the.
No, I don't think that's really correct. We'll come to that later. I don't think that's accurate, right? Now, let's look at the Z transform, right? So, we have the Z plane. This is the Z plane. See, please note that a region of convergence may be neither right-sided nor left-sided. So, we have not considered that possibility as yet, right. So, before we come to general conclusions about the nature of functions, we must remember that the statement that we made just now was only where the function was strictly right-sided or strictly left-sided, and therefore, the ROC was also strictly left or right-sided. Yeah. Now, in the Z plane, you see, remember we had this point Z equal to mod A. So, this is the origin of the Z plane, Z equal to 0. and let's assume z equal to a is somewhere here. Yeah. Now a could be complex in general, right? So we have this circle. So now instead of a vertical line, we have a circle. And there are two possible regions of convergence, either to the interior of the circle or to the exterior of the circle. Yeah. So interior, ROC, let's call it ROC2. And remember, this corresponds to the sequence minus a raised to the power n u minus n minus 1. And exterior ROC, ROC1 corresponds to the sequence a raised to the power of n un. All right. So here, what is the corresponding statement in the Z transform? When you have a region of convergence which is to the interior of a disk or a circle, then the corresponding sequence is left-sided, interior left-sided, exterior right-sided. Again, a region of convergence might be neither exterior nor interior. It might lie between two disks, between two circles. In that case, we need to treat the situation separately. In fact, in a moment, we shall be able to extend our arguments to that situation. Actually, what we have done here is to consider the most primitive kind of function or sequence for which we have a Z transform, namely the exponential function or the exponential sequence. So what we have done is we have considered the Laplace transform of an exponential function either right truncated or left truncated. Similarly, we have considered the Z transform for sequence, an exponential sequence, either right truncated or left truncated. And we have been able to establish the corresponding regions of convergence. Now we shall like to bring out a new concept, both the Laplace transform and also in the Z transform, that relates to the expression itself, right? So let's write both of them together to see what I mean. You see, let's write down the Laplace transform that we've been discussing, 1 by s minus 2. And let's write down the corresponding Z transform, 1 by 1 minus a Z inverse. Now, what happens to this expression at the point s equal to 2? It goes towards infinity, yes? The denominator goes to 0 and therefore the magnitude goes towards infinity. What happens to this at the point z equal to a? The same thing. It blows up towards infinity, right? Now visualize this S plane or the Z plane as the horizontal ground, right? And the magnitude as a tent that you place on the ground. What would happen to the tent at the point S equal to 2? It would appear to rise towards infinity. So as if there's a pole holding the tent at that point. That's the reason why the point S equal to 2 is called the pole of this function. And the point Z equal to a is called the pole of this Z transform here. It's a point where the tent appears to rise infinitely as if held by a pole. Is that right? Now, let us focus our attention on that class of Laplace transforms or Z transforms which have a numerator and a denominator, both of which are polynomials in S or Z respectively. Now, when you have polynomials in S and Z, the polynomial in the denominator would have its roots which we will call poles, because at each of those roots, unless they are cancelled, so we will assume the polynomials are in, we'll assume that the expression for the Laplace transform or for the Z transform is in lowest form or in reduced form. That means if there are any common factors between the polynomials in the numerator and denominator, they have been removed, right. Once we do that, then if we look at the polynomials in the denominator, all the roots of the polynomials in the denominator correspond to poles, because those are the points where the function rises to infinity, right. And what about the role of those points at which the numerator goes to 0? At those points, the function itself comes to 0. So they are called the zeros of the function, right. So we have poles and zeros. So for example, s minus 3 by s minus 2 has a pole at s equal to 2 and a 0 at s equal to 3. And similarly, if we have 1 minus say a1 z inverse divided by 1 minus a2 z inverse, 1 not equal to a2, then we have a pole at z equal to a2 and a 0 at z equal to a1. Yeah. Now, so far both the examples that we have considered are functions where there is a single pole. So you see, now what we are going to do is we are going to relate the possible regions of convergence to the poles and zeros. In fact, we shall see that the regions of convergence are ultimately governed by the non-cancelled poles, whether we are talking about the Laplace transform or the Z transform, right. So in the next lecture, we shall continue by realizing the relationship between the poles and zeros and the region of convergence. Well, don't leave. There are a couple of announcements. Okay. One announcement, of course, I assume there is no together, and to recall what we were doing in the previous lecture, we had looked at the idea of a pole, and we had considered a situation where the Laplace transform has a single pole, right. Now we will take further the situation where the Laplace transform has a single pole, or where the Z transform has a single pole, but we will take it further after we derive a property of both the Laplace transform and the Z transform. The idea was we decided we look at the properties together, because a lot of us have experience in using the Laplace transform, but not the Z transform, and it is helpful to look at the two transforms in a common light. Yes. So we shall establish the property of differentiation. Yes. What happens when we differentiate the Laplace of the Z transforms? We shall first consider it for the Laplace transform. In fact, this would be a generalization of the corresponding property for the Fourier transform. So let's assume that a certain xt has the Laplace transform capital X of s, which is therefore given by minus infinity to plus infinity integral xt e raised to the power minus st dt with a certain ROC.